Hello class, Mr. Pope here. I thought I'd just upload a video, seeing as I'm not entirely sure how well the PowerPoint will be absorbed. Just wanted to say hope you're all keeping well. And I'm just I'm not sure how long this video is going to be. If it takes an hour, it takes an hour, but I just want to go through all the chapter 1 stuff fairly briefly with a few examples just to get the key points across. So let's start with proof by contradiction. Okay, it's really easy. Proof by contradiction is a form of algebraic proof where the long and short of it is you have an original statement, a statement you're trying to test, or prove rather, and what you do is you assume the opposite or the inverse is true. So say for example you're trying to prove n is greater than 2, then the opposite of that would be n is less than or equal to 2. You're essentially, your initial starting point is you assume that the original statement, you're going to take the opposite or the inverse position and assume that's true. And then what you do is you work algebraically and systematically, and hopefully you should reach a contradiction. Okay, and then when you reach that contradiction, and the idea is that you've worked perfectly up to that point. So if you reach a contradiction where the case cannot be true, then the only thing that could have potentially been wrong was the initial assumption must be wrong, and therefore that concludes the proof. As a little style note, you can either put a little square like that to say the proof's done, or in some older textbooks you might say QED, which stands for Quod Erat Demonstrandum, which is Latin for which needed to have been shown or demonstrated. That's not really necessary for this course. I think if you can provide a sound logical argument that's structured and all steps are laid out, then you're doing well. So okay, what would potentially be an example of this? And the classic bread and butter example would be to the proof that root 2 is irrational. Okay, this is old chestnut stuff in mathematics. So if I wanted to prove that root 2 is irrational, then by contradiction assume that root 2 is rational, because that's the opposite of being irrational. And what are rational numbers? Rational numbers are the form a over b, where a and b, whoops, wrong symbol, a and b, I don't know why I put an uppercase b, silly boy, where a and b belong to the set of integers, and a and b are co-prime. Okay, so what does this mean? This is kind of like the extra details on the side. So the initial statement is that root 2 can be written as a rational number, and the way to express that mathematically is say that root 2 is some a over b, where a belongs to the set of integers and a and b are co-prime. So let's break this down. What is it I've just said? Well, this symbol here is set notation, and it reads belongs to the set of, and this z with the extra line, this italicized z, is the set of integers. Okay, so what that's essentially saying is A and B belong to the set of integers. And then this idea here of being co-prime is essentially saying they have no common factors, or rather they have no common prime factors, even though they might not necessarily be prime themselves. So I'll give you an example of that. 8 over 15. So those two are co-prime because 8 isn't prime and neither's 15, but because they have no common factors, this fraction can't be simplified anymore. So we would say 8 and 15 are co-prime. So the numbers themselves don't necessarily have to be prime, but the fact that they can't cancel down means that they are co-prime. So it's a little subtle distinction there. Okay, so what would my working be? Let's try a different colour. Well, what could we do here? Well, root 2 times b would equal a if I multiply by b both sides. And that's totally fine. And to be fair, we've divided by b over here, so really the extra addendum is that b cannot equal to 0. And also, a can't equal to 0, otherwise we're showing that root 2 equals 0, because 0 over anything is just 0. So, I mean, that was given, but we might as well do it for completeness. So, let's get back to what we were doing. So if root 2b equals a, that's fine. Then what might the next step be? The next step might be to square both sides. So square the left-hand side, we get 2b squared. And on the right-hand side, we get a squared. Okay, now here's the deal. What can you tell me about the number on the left-hand side? Because it's 2 times by an integer, then this thing must be even. And now that means the right-hand side must be even. And that means if a squared is even, then a must be an even number. Because an even times an even would give an even, and an odd times an odd would give an odd. This number is being squared, so it must be the number times by itself. So it's either two odd numbers, where they're both the same to get an odd, which isn't happening because it's even, or it's an even times an even, which gets another even. And now the trick here is you can write a as something else to, let's say, n, where n belongs to the set of integers. So for any integer n, if I times it by 2, that's an even number, so a can be expressed as 2n. So, what does that mean? That means 2b squared equals a, which is 2n all squared. Can you see where I'm going with this? And then if I expand the right-hand side, 2n squared is 2n times 2n, which is 4n squared. And now if I divide by 2 both sides, I get 2n squared equals to b squared. And now look what happens. Now we've got a similar argument, but this time it's on the other side. If n is an integer, n squared is an integer, but 2 times an integer means that the right-hand side is even, which means the left side is even as well, which means we can deduce from that that therefore b is even. But look, there is a contradiction. Why is there a contradiction? Because if a is even and b is even, that means they both are even numbers and therefore they have a common factor of 2. If I have an even number and another even number, they're always in the 2 times table. Why is that a problem? Because look at our initial assumption. We said that a and b must be co-prime. Okay, so on that technicality, because a and b are supposed to be co-prime, but when we assume that root 2 is rational, we end up with a and b both being divisible by a common factor, i.e. not being co-prime. Therefore, we've reached a contradiction. So, this contradiction, a and b can have no common factors, or should I say no prime common factors, but they appear to have a common factor of 2. Therefore, A and B are not co-prime when they should be. Therefore, root 2 is not rational. The underlying assumption is not true. Proof completed. Okay, so this is a very classic proof, and in actual fact, you can do it for any number that's any surd, a non-square surd, and you do it in a similar way. So let's have this being example 1, and let's have example 2 down here. Okay, so what do I mean by that? Well, let's say I'm trying to prove that root k is irrational when k does not equal some integer squared, where n and k belong to the set of integers. Okay, this is what I'm trying to prove. So, for example, if I've got root 1, I've got root 2, I've got root 3, root 4, root 5, root 6, root 7, root 8, root 9. Right, because 1 squared is 1, that's rational, because that's just 1. Because 4 is 2 squared, that's rational. Because 9 is 3 squared, that's rational, and so on. I.e., I can turn all of these perfect squares, I can evaluate these surds fine. And what I'm claiming is all these other surds, where they're non-squares inside of the radicand, then those are irrational. Okay, by the way, this thing here, that symbol is called the radicand. But you don't need to know that, it's just, yeah, anyway, that's what it's called. Americans call surds radicals. Some of them do anyway, some of them call them surds, it's quite rare. It's by the by. Anyway, so how would I prove that any non-square, a surd of any non-square integer is irrational? Well, same proof as before. So we start off with assuming the opposite is true. So assume, some people say negation, the not case, some people say the inverse. It honestly doesn't matter, just assume the opposite. So let's say root k can be written as a rational number where a and b both can't equal to 0, a and b belongs to the set of integers, and a and b are co-prime. Okay, so it's the same setup as before. Neither a nor b can be equal to 0 for obvious reasons, because we're dealing with non-zero squared surds, and clearly 0 is 0 squared, so that's not going to work. And also b can't be equal to 0, otherwise we've got a fraction that can't be resolved. A and b are integers, because that's the whole point of rational numbers. Is there quotients or fractions with integer denominators and numerators, and a and b are co-prime, i.e. I've simplified this fraction down. So same deal as before. If I multiply by b both sides, I get root kb equals a. If I square both sides, I get kb squared equals to a. And it's a very similar proof here, but this time, on the left-hand side, look, I've got k times by an integer, haven't I? I've got k times b squared. So that means if I do /k, that means the left-hand side is divisible by k. And that makes sense because it's k times a number. It's in the k times table. So that necessarily means that a is divisible by k. Okay. Now, what does that? So a is divisible by k. So that means we can write a as some n times k. It's a multiple of k. All right, and then I'll substitute, oh sorry, this is squared. And now I'll just sub it back in. So a squared is nk all squared, and this equals to kb squared. If I square the right hand side, I get n squared k squared. This equals to kb squared. If I divide by k both sides, I get b squared equals n squared times k. I'm allowed to divide by k. I should have made this clear. That k belong to the set of positive integers up there. And in actual fact, I won't use n because I've used n before previously higher up. Let's use d. So that's dk, d squared k, dc. Okay, fine. Fine. And now look. We run into a similar problem. The right hand side is d squared times k. D is just is an integer, and k is an integer, so the whole right hand side is just an integer of k, so it's divisible by k, which means b squared is also divisible by k, which means that if b is divisible by k, then b equals some multiple e of k. And now can you see the problem? We've just proven that a and b are multiples of k. Therefore, they are not co-prime because they have a common factor of k. They are not fully reduced. So in actual fact, this proof has now been done. So for similar reason, I'm just going to put ... because I'm incredibly lazy. But essentially, what if you were to do it properly, you'd write a sentence to say contradiction because, and you'd write the stuff out, and then end proof with a square. But essentially, that is what you needed to do. So proof by contradiction is fairly straightforward. You just have an initial statement that you're trying to prove. You assume the opposite, or you can assume the negation or assume the inverse. It honestly doesn't matter. I mean, there are slight subtle differences, but at A level you're not going to be punished for it. That's not the case. The main point is you formed a logical argument. For me, I think that the more important thing is you have carefully defined these stipulations here, and these things here and these things here. You might think like, oh, that's just stuff I don't need to worry about. In actual fact, in both of these proofs, I referenced what these things depended on in both proofs. They're incredibly important. Without those, you can't actually move forward. So yeah, having like a clear set of working, making sure you've got all the provisions and the necessities you need and for it to be done. And then when you reach a contradiction where it doesn't make sense, or rather you start repeating yourself, or you run into something that clearly doesn't make sense, when you start doing things like proving 2 equals 1, for example, then you've run into a contradiction. You run into a mistake, essentially. You've run into something that just can't be true, and it's contradicted what you've initially assumed to be true, which in this case is the blue stuff that's highlighted orange. Okay, so that's pretty much proof by contradiction. I want to whiz on and do some algebraic fractions. A lot of this is from GCSE, and you can look at various websites on how to add, subtract, multiply and divide algebraic fractions. But pretty much, let's start with the simplest case, and we want to simplify algebraic fractions. Well, that's easy. Let's suppose I've got x squared plus 5x plus 6, and this is all over x squared plus 6x plus 8. Well, if I want to simplify this, it's really easy. I'll just factorise top and bottom. The top factorises to x plus 2 times by x plus 3. The bottom factorises to x plus 2 times by x plus 4. The x plus 2's cancel top and bottom, and you're left with x plus 3 over x plus 4 as your final answer. Okay, so there is no technique here really. You just have to spot. Okay, you have to factorize. Okay, what you cannot do, what you mustn't do. No, and some of you will do this because I don't know why. I really, really dislike putting down common misconceptions because I always like to think you've never learnt that from me, you've done it yourself. When I start seeing things like this, let's say x squared plus 7x plus 3 all over, say, x squared plus 4x minus 5, I don't want to be seeing this. I don't want to be seeing the x squareds cancelling. So you're left with 7x plus 3 over 4x minus 5, and then seeing stuff like the x's cancelling here. So you've got 7 plus 3, which is 10 over 4, so it becomes minus 10. Yeah, I don't want to see this. I really don't want to see this. If you know what, if you really, really, really don't know what you're doing, then my plea to you would be the following. If you substituted in a value of x on the left-hand side, would it equal the right? Can you find a value of x for which this doesn't work? And the easiest one for me is when x is 0, because it becomes 0 squared plus 7 lots of 0 plus 3 on the top, which is 3, over on the bottom 0 squared plus 4 lots of 0 minus 5, which is minus 5. Clearly, minus 3/5 does not equal minus 10. Right? You've got to stop doing this stuff. Maybe you guys won't ever make this mistake, but I'm really getting ticked off with so many sixth formers just making this mistake. It's dumb. Don't ever do it again. Right. So, simplifying. That's probably the simplest one. No pun intended. Next thing I wanted to talk about is addition and subtraction. And this is really easy as well, because all you have to do is get a common denominator. So let's say I've got x plus 3 over x plus 4, and I want to add 3 over x minus 5. Then this is just going to be all over x plus 4 times by x minus 5, common denominator. And then this fraction is missing the x minus 5. So I need to times the top, x plus 3 times the x minus 5, plus stays the same, and then this fraction is missing the x plus 4 on the bottom, so I've actually got 3 lots of the denominator multiplied across, so it's x plus 4. It works in the same way. I mean, look, all the rules that you knew for normal fractions. If I had 2/3 plus 3/5, well, that's clearly going to be both over 15. I've got to scale this up by 5 top and bottom, scale this up by 3 top and bottom. So this is 10 plus 9. It's the same deal. Like what you were doing with numerical fractions is exactly the same for algebraic ones. The rules do not change. It just looks more trickier. Anyway, so if we deal with this, we're going to get all over x plus 4 times by x minus 5. The left-hand side, if you expand that really quickly, is x squared minus 2x minus 15. And on the right-hand side, if you expand it, that's 3x plus 12. Now, minus 2x plus 3x, that's going to be x squared plus x, and minus 15 plus 2 is going to be minus 3. As far as I'm aware, this doesn't factorise on the top, so we're going to have to leave it as that. You can't simplify any further. Okay. Right, adding and subtracting fractions, really easy. Multiplying and dividing fractions, it's exactly the same. So if I wanted to multiply or divide by algebraic fractions, it's exactly the same as how you were doing it at GCSE. So same numbers still. Let's say I wanted to do x plus 3 over x plus 4, and now I wanted to multiply that by 3 over x minus 5. Same deal. Top times the top, so that's 3 lots of x plus 3, all over bottom times bottom, which is x plus 4 times x minus 5. That's it, done. Not a problem. Suppose I wanted to divide now. So let's suppose I've got x plus 3 over x plus 4, and now I'm dividing by 3 over x minus 5. Well, that is the same as keep the first fraction, x plus 3 over x plus 4, you change the divide to a times, and you reciprocate the other fraction, x minus 5 over 3. and you deal with that in the same way. So x plus 3 times that, so you can have x plus 3 times by x minus 5 all over 3 times this, that's 3 lots of x plus 4. Done. Easy peasy. Okay. Multiplying, dividing fractions, causes, adding and subtracting fractions, causes, simplifying fractions, causes. It's really important you know how to factorise polynomials for this, and you just have to be really careful and not make any mistakes. It happens all the time. I constantly make mistakes. Don't worry about it, just check your work. So as far as I'm concerned, that's pretty much 1.2 done. Okay, what else have we got? Partial fractions, groovy. Okay, right, so let's tidy this up a little bit. So let's get this down here. Okay, so let's tidy up. So 1.1 was up there, 1.2 is over there. I will publish these notes as a PDF on Google Classroom. I'm just going to pause the video because my robot Hoover has just started up. Be back in a sec. Right, sorry about that. Where were we? Okay, so partial fractions. Okay, so what's that? 1.3. Okay, so what do we mean by partial fractions? Okay, so consider the case when I add two fractions together. Let's say I've got 3 over x plus 2 minus 2 over, let's say, x plus 1. Okay, so how would you do that? Well, you would have all over x plus 2 times by x plus 1, and you'd have x plus 1 times 3 over here, minus, because there's a minus sign there, and x plus 2 times by this thing, so there's 2 lots of x plus 2. Okay, so what would happen? I'd have 3 times x minus 2 times x, that's a single x, and 3 times 1 minus 2 times 2, so that's 3 minus 4, so it's going to be minus 1. So the whole fraction becomes x plus 2 over x plus 1. And now, so when you're adding and subtracting fractions, you're going from two separate fractions to a combined fraction. What partial fractions are going to do is it's going to take a combined fraction like this and split it up. It's going to be the reverse process. It's going to be splitting up into multiple things. Okay, so, okay, how would we do this? Well, the first thing we do is, okay, first step is we always try to simplify first. And there's a couple of tricks you can do. You can factorize. The other thing you can do is you can do algebraic long division when the order or powers of x in the numerator is bigger than the order in the denominator. So what do I mean by that? Well, let's say I had the fraction x squared plus 2 all over, say, x plus 1. So because there's a squared power in the top is of order 2. And on the bottom, there's an x to the 1 on the bottom. So we've got a quadratic over a linear term. So because the order is higher on the top, the numerator, than the denominator on the bottom, we should really try algebraic long division first before moving on. So let's do that. So just a quick reminder, x squared plus 2 we'd write as x squared plus 0x plus 2, and this is being divided by x plus 1, so there's x plus 1 there. How many x's go into x squared? Well, that would be 1 lots of x, and then I take this x and I multiply it by x plus 1 and put it underneath. So x times x plus 1 is x squared plus 1x. Then I subtract, the x squared's cancelled, 0x minus 1x is minus x. Bring down the plus 2, so I now have minus x plus 2. And then it repeats itself again. How many x's are in minus x? Well, that would be minus 1. And then if I do minus 1 times by this stuff, I'll get minus x minus 1. Minus x minus a minus x is 0. 2 minus a minus 1 is 3. Remember, a minus is a positive because I'm doing 2 minus negative 1. So it's going to be 3. Okay, what does this tell me? This tells me that x squared plus 2 over x plus 1 will equal the top, which is x minus 1, plus the remainder, which is 3, over the thing I divided by x plus 1. And then if you're going to do algebraic partial fractions, then it's this thing that needs to be split up. Okay, so you can actually, and then look, by doing that, this fraction, there's a power of x to the 0 on top, i.e. there's just constants, and there's x to the 1s on bottom. Now the denominator's order, or powers of x, is now bigger, so we can now progress with partial fractions. So always try to simplify. If the order of x's is on the top and the numerator is bigger than the order in the denominator, then you need to do algebraic long division to simplify it, and then what we're about to do, partial fractions, you do on that leftover bit, the remainder over the divisor. So let's just crack on. How do we do this? Well, there's lots of ways. So let's take a fraction. Let's try 1 over, let's say, x squared minus 1. That's a classic one. Okay, so first of all, we're going to factorise. So what does that mean? It means the bottom is going to be x minus 1 times by x plus 1. So partial fractions decomposition would mean that it's going to be something over x minus 1 plus a constant over x plus 1. And you've got to notice, when you break down this partial fraction stuff, the order of the top can be at most 1 less than the order of the bottom. So because this is a linear term, i.e. x to the 1 on the bottom, this must be x to the 0 on the top. Okay, similarly, this is an x to 1 on the bottom, this must be an x to the 0 on top. Okay, if this was an x squared on the bottom and it didn't factorise, then I could have a linear term, for example, bx plus c. And we'll do that in a second, but let's keep it simple. Okay, the point is the top cannot be bigger than the bottom when we're dealing with this stuff. Okay, now there's various ways of doing this. Black Pen, Red Pen likes to jump the gun a little bit. It's a YouTube channel, Black Pen, Red Pen. Quite good for integrals and stuff. Personally, I think he goes too fast on some bits and too slow on other bits. And his accent does annoy me a little bit. I think he slurs words a little bit. But then, in all fairness, he's clearly not a native English speaker, and I think it's very commendable for someone that's not an English speaker. Well, I just think it's commendable to teach that high level of maths in a foreign language. It's not your first language, so you know I thoroughly encourage you to watch his videos. Okay, so I have got to deal with this thing. How am I going to do with that? Well, what I'm going to do is I'm going to multiply everything by this x plus 1 and x minus 1. So the left-hand side will become 1, and the right-hand side, well, the x minus 1 will cancel with the multiply by x minus 1, but I'm going to be left with lots of x plus 1. Yeah, because if I've got x minus 1 and this was all over x minus 1, all I've done is multiply by this x plus 1, x minus 1 on the top. So what happened? The x minus 1's cancel. Essentially, I'm eliminating this fraction stuff. There's going to be no more fractions. Then similarly, the next term is going to be b lots of x minus 1. Okay, now there's various ways. There's two ways, in actual fact, that I like to use. One of them is comparing coefficients, because I want to find values of a and values of b for which this is true. So if I expand this, I will get 1 equals ax plus a plus bx minus b. And the way this works is if I look at the x coefficients, I've got no x's on the left-hand side, I've just got the number 1. On the right-hand side, I've got a plus b lots of x. So that's my one simultaneous equation. Then if I look at my constants, I've got a 1 on the left-hand side, and then I've got an a on the right-hand side and a minus b on the right-hand side. And now we can solve fairly quickly what's going on here, because if I add these two things together, I'll get 2 equals 2a, so a equals half. And then clearly a plus b equals 0, so then b must equal minus a half. So this will tidy up quite nicely as a is 1/2, so that's a half x minus 1 like that, and b is minus 1/2. And you're probably thinking, oh, that looks a bit dirty. Why is there fractions and fractions? Well, the way to deal with this is the numerator stays on the top, so that'll be 1 over 1 over. The minus still stays. The denominators still stay as they are, but this time, look what I'm going to do with the 2's. I'm going to put them out front, in front of the brackets. So this is actually 1 over 2 lots of x minus 1 minus 1 over 2 lots of x plus 1. So actually, I've now successfully decomposed 1 over x squared minus 1 as 1 over 2 lots of x minus 1 minus 1 over 2x plus 1. The other method, really quickly, is when we use substitution. Okay, and this is generally the quicker way, but it doesn't work all the time, and I'll talk about when it doesn't work. So what I want is, suppose I want the a term to disappear, so I'm just left with b's. What must x be so that this term disappears? Well, if x equals to minus 1, then the left-hand side is 1, this term disappears, and I've got b, lots of minus 1, which is minus 2, so I've got b times minus 2 is 1, so b equals minus 1 over 2. And indeed, that's what b was down here, so that's looking good. And then by similar logic, what can I substitute in to make the b term disappear? Well, that's x is 1. And when x is 1, the left-hand side is 1, the right-hand side is a, lots of 1 plus 1, which is 2, and we've made the b term disappear, and if a times 2 is 1, then a is a half. And that is totally consistent with what we've done before. So, what's the point of that? Well, because later on we'll be dealing with integration, and suppose I wanted to integrate 1 over x squared minus 1. That's not particularly easy to do. Unless you know hyperbolic functions, you're going to have to leave it like that. But what you can do for A-level mathematicians is you can integrate this thing instead. You'll learn how to integrate simple algebraic fractions like that. Okay, they're just going to be logarithms. So actually, I think that's, if I was going to just do it by eyeball, this is going to become ln of x minus 1 over x plus 1 square rooted plus a constant. And later on you'll figure out why that's the case. I'll no doubt talk to you about that in about November, December time, maybe January, depends how slow or quickly we go. But yeah, so one of the main reasons for getting partial fractions down is it's going to make your integration life a lot easier. It's a nice bit of algebra. It's really easy to do. The two main schools of thought are substitution and comparing coefficients. I know red pen and black pen do this weird like substitution beforehand, and they kind of do it by inspection. It's actually quite clever. I haven't got my head around it just because I just think, yeah, okay, it's just a different method. It's similarly how they integrate by parts, and they do this DI method, which isn't just like a sped up version of integration by parts. And I've kind of poo-pooed it off because it seems very much like they're cutting corners. And I like to do things slowly and properly, but never mind. So, okay. So what's the deal between comparing coefficients and substitution? Because these are, as far as I'm concerned, they're like the two main bread and butter methods. So comparing coefficients will always work, but it's slower. And as you saw, I had to build up a chain of simultaneous equations, and because there was only A and B, it didn't take too long. But suppose there were A's and B's and C's and D's and E's and so on, it could take a long while. Substitution is quicker, but it doesn't always work. And when I say it doesn't always work, it does work, but it will work up until a point. There'll be a bit where you can't spot a substitution that will eliminate for one particular unknown. So my advice is to be flexible between the two, and really that flows on quite nicely to this thing. when you have to do partial fractions with repeated factors. So what on earth does that mean? So was it 1.4? I've forgotten already. Yeah, 1.4. Okay, so what do I mean by repeated factors? So 1.4 when you're doing partial fractions by repeated factors. Okay, I cannot spell. Okay, so imagine we've got the fraction, let's say 2x plus 3 over, and now let's say x squared plus x plus 3. Okay, now here's the deal. This factor x is being repeated twice. So the way to get around that is this will be some constant over x squared plus some constant over that x plus some constant over the remaining factor x plus 3. Okay. Now, here's the critical thing. You're probably thinking like, okay, well, Mr. Pope, well, this has an order of 0 because it's a constant, and this is an order of 2. So can't you have an ax plus b over here because this is order 1 and that's technically smaller than order of 2? No. Okay, it's if you can reduce the power of it, it's the order of once you've reduced it, because technically this is x squared. This is an order 1 polynomial. If I had something like x squared plus 3x plus 4 that can't be factorized, then this whole thing is of order 2. Okay, so it's like the most you can reduce it down by. You know, actually, here's the thing. You could, if you really wanted to, you could have ax plus d there, for example, but I know d is going to equal to 0. So, I mean, you can include it, but you're just going to get d is equal to 0 and you're wasting time a little bit. But you know what? We'll leave it in there just to prove a point. So, okay, let's crack on. First thing we're going to do is we're going to multiply both sides by the denominator. The reason I do that is because there's order 1 on the top, and this is clearly going to be a cubic on the bottom, so the top definitely is smaller than the bottom. Okay. So I'm going to have, on the left-hand side, I'm going to have 2x plus 3 equals, now I've got ax plus d, lots of, well actually no, the a's not going to be the d's not going to be the 0, it's going to be the a is going to be the 0, because there's going to be no x terms, but anyway, we'll get there. It's just going to be a constant of x squared. So this is going to be just x plus 3 here, because when I times by x squareds, the x squareds cancel out. Now the middle term is going to be bx times by x plus 3. Why? Because if I times this by x squared, one of the x's will cancel, and then I've got the x plus 3 to multiply by. And then I've got the c times by x squared at the end. Right, now here's the deal. We're going to do a mixture of substitution and comparing coefficients, and this is why substitution is quicker, but it's not necessarily going to, well, it's going to work up to a point. Now I notice that this term, the b term has an x and the c has an x term, so I can spot straight away, if I let x equal to 0, the left hand side becomes 3 and the right hand side, this term and this term go, which is great, and this term becomes 0 times a, which is 0 plus d, so that's d, lots of 0 plus 3, which is 3, so I've got 3d equals 3, so d equals 1. Lovely, 1 down, 3 to go. Next up, what could I also substitute in? Well, let's keep the x's as they are. I could substitute in x equals minus 3. Why? Because that would make this a 0 and that would make this a 0, and I'd be left with the c term. Okay, so when x is minus 3, the left hand side is 2 lots of minus 3 plus 3, which is a single minus 3. This disappears, I'm left with c. Minus 3 squared is 9, so 9c equals that. So I'm going to get c equals minus 1 over 27. Not nice, but if that's what it is, that's what it is. Okay, now here's the deal. This is when x is minus 3. This is when x is 0. Can you spot that because this b has a shared factor of x's and x plus 3's, there isn't going to be a substitution to eliminate just for b. So we're stuck. So unfortunately, we're going to have to now abandon the substitution method and now go over to comparing coefficients. But at least it's a little bit easier now. Okay, how do I know this? Well, okay, let's just do it in turns. X squareds. There's 0x squared on the left, but there's going to be an ax times an x, which is an ax squared there. And we have a bx times x, which is going to be a plus bx squared there. I don't know why I put the x squared, so we'll just leave them as it is. Oh, and there's a cx squared over there, so plus c. Well, in actual fact, I know what c is. It's minus 1 over 27. So this I can get rid of and put minus 1 over 27. So in actual fact, a plus b equals positive 1 over 27. Nice. Simultaneous equation 1 done. Next, let's look at the x's. Well, if I expand this carefully, I'm going to have ax times 3, which is 3ax. I'm going to have a d times x, so plus a dx. And I'm going to have a bx times 3, which is going to be a plus 3bx. And then that's it. And this equals the amount of x's on the left-hand side, which is 2x. Get rid of the x's because it's only the coefficients I'm looking for. Don't know why I wrote them down. And now let's consider. Well, d is 1. I've worked that out. So if I get rid of that 1, so minus 1 from both sides, I get this equals to 1. So 3a plus 3b equals 1. If I divide by 3 both sides, I get 3b, I get a plus b equals a third. And now, look, we've got a bit of a consistency here, haven't we? Have I done this wrong? How can I have a plus b equals 1/27th and a plus b equals a third? Alright, let's backtrack. X squareds. I'm going to have an a, lots of x squared there. B plus c. So I'm going to have a plus b plus c. C is minus 1 over 27. Oh, you silly boy. Minus 3 divided by 9 is minus that's a third. You silly boy. That's fine. So I'm just silly and I can't divide by numbers. Okay, so actually by looking at x's, that hasn't really told anything. So let's have a look at the constant terms. Oh, you silly boy. Okay, constant terms. So on the left-hand side there was 3. On the right-hand side there'd be d times 3, which is 3d. And there won't be any other constant terms on the right-hand side. So we'll get 3d equals 3, so d equals 1. Ooh. Yeah, which is what we've got already. Okay. Interesting. Okay. We've got a plus b. What can we do here? Well, I know a is going to be 0. If a was 0, b is going to equal a third. Just thinking how you'd prove that. Let's have a think. Oh, that's why. Okay, the reason why it can't be ax plus d is because if you had ax plus d, then this would be ax over x squared plus d over x squared. And then ax over x squared is just going to be a over x plus d over x squared. And this a over x would essentially just get absorbed by the b over x. We've already covered it. So that's just stupid. We don't really need it. So in actual fact, the ax isn't needed. So then b is a third. So how would I write? How would you write? So this is a. No, what did I say? This is d. This is d, isn't it? This is d. So d is 1, so it's going to be 1 over x squared. plus b. Well, b is a third, so it's going to be plus 1 over 3x. And c is minus a third, so it'll be minus 1 over 3 x plus 3. Okay. Yeah, that's pretty much it. So 1 over x squared plus 1 over 3x minus 1 over 3, lots of x plus 3. If you're, I think my tip would be, if you're unsure of what power you can have at the top, maybe see if you can split it up. So there, I thought potentially it could be an ax plus d over x squared, but then that's the same as ax over x squared plus d over x squared. And although this gives me the thing over the x squared, this is actually an a over x thing. And yeah, I've already considered my over x fractions there, so that's just a bit redundant. So I'll just become an a plus b there, and then yeah, I already know that that's a third, which is what I had over there in the top right. So yeah, it does work out. You just have to be consistent. Okay, in general, so what happens if you had something like, I don't know, 3 over, let's say, x cubed and then x minus 4 squared? Then you would need a constant over x cubed plus a different constant over x squared plus a different constant over x plus a different constant over x minus 4 squared plus a different constant over x minus 4. And yeah, that just is horrible. If you want to do it and convince yourself it's the right answer, that's fine. If you want to check you've got the right answer, what you can do is then, once you've found this fraction, all the numbers for which it works, you then can add them all together again. And then once you simplify, and if you do get that, then you've got the right answer. But you should get the idea of what you need to do there. Right, what was the last thing? Oh, algebraic division. Oh, lol. Well, here it is. I've already done that. So this is 1.5 algebraic division. Yeah, I mean, we did this last year, or this year. Oh, heads all over the place. Yeah, so there you go. I think I've covered everything. Hope to see you guys soon. Peace out.